Okay, let's begin. Last time we started talking about equations. We talked about what they are. We spoke about linear equations, nonlinear equations, and now we're specifically focusing on quadratic equations. So still in 1.5, we'll continue to talk about equations. And I want to talk, so we're still in the section on quadratic equations. So you might recall, this is just an equation of the form ax squared plus bx plus c equals 0, where your a is not equal to 0, and your a, b, c are constants. And last time we looked at I don't want to say the main way. Huh? So, I don't want to say the main way here, but maybe the preferred way. It's by factoring. Okay, so we also looked at what it means to solve something by factoring. Bring everything to one side so that the other side is 0. Factor the left side and then set each factor equal to 0. That's taking advantage of the zero factor property, one of the properties of equations. However, sometimes this doesn't work. And so now let's discuss some other options. So, and we looked at a bunch of ways to factor something, both when the a is 1 versus when the a is not equal to 1, and you use the AC method or trial and error. But sometimes you can't factor these guys at all, and so we need to know how to deal with those. And so one option is called completing the square, which we're not going to spend a lot of time on that for this particular topic. When we start talking about circles, we will revisit this. But I'm just going to go through enough of it to derive some things for you. So completing the square is a method to get a complete square out of this quadratic. That's kind of like your a plus b all squared, or your a minus b all squared, which you know how to deal with. And that will actually make it easier to solve. So we kind of notice the pattern with complete squares. So maybe I should write that down. Here's a pattern that we know with complete squares. You take a plus b all squared. What is that equal to? Ask that on like 3 quizzes in a row now. Interesting to see how many people get that wrong 3 times in a row. But, anyway, if you were to say, replace this with x and that with a, just for you to be able to see something that I want to point out here. So x, think of it as the variable, a, think of it as a constant. This would be x squared plus 2ax plus a squared. And what I want you to notice is that the guy here is 1/2 the coefficient of x all squared. Right? Notice that if I look at the coefficient of x, I take half of that. Half of 2a will be a. And so the last term is just a half of this all squared. And so what we can do is we can take advantage of that little pattern to create a complete square even though we might not have one in the beginning. So if we start with ax squared plus bx plus c equals 0, we can do the following. Let's factor out an a from the first two terms. And let's try to create that pattern inside the parentheses. So we have x squared plus b over ax. Now what I want to do is create a constant term that is 1/2 of this all squared. And so we do that little sneaky trick math people do all the time. We add and subtract something. We add in something that we want, but of course we can't change the value, so we subtract it again. So we can add and subtract the square of 1/2 of this guy. So we take b over 2a, b over 2a. We add and subtract that. Now what's going to happen is the first three terms will become a complete square, just like this formula. You will see it become x plus b over 2a all squared. This guy left over is going to be your minus b squared over 4a squared. And we're multiplying it by a. Now it turns out, now I've created a situation where I can isolate this term and inevitably solve for the x by isolating that term much easier. So let's actually do that. By the way, this move, what I just did here, that's called completing the square. So completing the square refers to this process that just happened right here. I add and subtract something convenient that makes the first three terms a complete square, because I took advantage of that pattern. Now let's actually start solving for x. Turns out it'll actually be easier now. I can distribute the a. So I have a x plus b over 2a all squared minus b squared over 4a, right, because the a's would cancel when I multiply out, plus c equals 0. So now what I'm going to do, since this is the one term that has the x in it, I can isolate everyone else. So I have a x plus b over 2a squared. Move this over, I would get b squared over 4a minus c. I could divide both sides by a, because I'm concentrating on solving for this guy. So I get b squared over 4a squared minus c over a. Remember, our a is not 0, so dividing by it is okay. We assume it's not 0. What I can do now is create a common denominator. Multiply this by 4a over 4a. That gets me the denominator of 4a squared. And on top, I would have b squared minus 4ac. Now to solve this, I'm going to take the square root of both sides. So that gives us x plus b over 2a equals, get a plus or minus, we discussed why that happens already, b squared minus 4ac all over 4a squared. So our x is equal to, move this guy over, minus b over 2a, plus or minus. There's a law for powers that says powers distribute across divisions. So I can separate this as b squared minus 4ac over, apply the radical to the bottom, I will get 2a. And then I can combine these, because now they have the same denominator. And ultimately, I get x has to be this guy. Now this guy is very important. It's called the quadratic formula. As you will notice that it does not assume that we can factor things. This will work for any quadratic in general, as you will notice. Now, of course, for us, it would matter if what's underneath the radical is a negative number, because that will create a complex number, which is not in our syllabus. But as long as what's underneath here is something that's 0 or positive, this expression will solve that quadratic. It will even work in cases where things can be factored. It's just that in that case, you wouldn't really use it. But ultimately, this gives us a way out of the case where we can't factor. So by completing the square, we can derive a nice formula. So this is called the quadratic formula. So this says if ax squared plus bx plus c is equal to 0, where your a is non-zero and your a, b, c are constants, then your x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So you don't really need to know how to derive this, but you should know this. It's called the quadratic formula. And we can derive it via completing the square. So you can either, if you want to solve a quadratic that cannot be factored, you can either go through this process with the particular numbers and solve it, and that's saying you're solving it by completing the square. Or you can just plug in these numbers into this formula, and that says you're solving by a quadratic formula. So last time we said there were 3 main ways to solve quadratics: by factoring, completing the square, and quadratic formula. Turns out that the quadratic formula and completing the square are kind of the same thing. The quadratic formula just brings you to the last step of the completing the square process. So a lot of people, rather than having to go through all this every time, they just memorize that and they just like, okay, this is where we're going to end up. We might as well just use that as a formula. Okay. So last class we ended with some examples. Wanted to solve for x, and we had 4 problems we were going through. A, x squared plus 5x plus 6 equals 0. B, 5x squared equals 20x. C, x plus 3x plus 2 equals 13. D, x squared plus 8x plus 1 equals 0. And we actually already solved these 2. So this one could factor very nicely, and so that one wasn't too bad. This one, we also solved it by factoring. The important thing to remember here is to not do something like divide both sides by x, because 1, you'd lose solutions. 2, you could be doing something illegal if your x is equal to 0, which is a solution. So again, you'd solve by factoring. The right thing to do is to bring everyone to one side, factor, and then use the 0 factor property. Don't start dividing and simplifying before you do that. And so now we are moving on to here to C. Okay, so how would we deal with that one?
adjust the parentheses first.
Okay. Huh?
You multiply x plus 3 times x plus 2 first.
Okay. Yes, that is what we do. We address a common error here. Common error. Students often try to apply the zero factor property when they don't have a zero. So a common error is to do something like set the x plus 3 equals to 13, or the x plus 2 equals to 13, or any such similar thing. You cannot do a maneuver like that if there isn't a zero on the right side. It is called the zero factor property for a reason. It has to be zero on the other side for you to do something like that. So we can't do that. It's very important that you know that's not something I would ever do. Okay. That being said, now you might say, what can we do? And so the right thing would be to expand this and regroup, bring everyone to one side as usual. So we just expand this, which would give us x squared, 3x plus 2x plus 6. And remember, our rule is to bring everything to one side, so we have x squared plus 5x. What would that be?
Minus 7.
Minus 7. Does that factor?
No.
Right, so now we try to see if this is a factor. We need two numbers that when you multiply give you minus 7. When you add them you get positive 5. 7 is a prime number, so 1 and 7 are really our only options here. But 1 and 7 can't really give you 5. So here you realize it doesn't factor. So once you realize something doesn't factor, that's the guy you go to. When it comes to a quadratic, you go to the quadratic formula. So here we would realize that x is equal to, what would the numbers be here?
Negative 5.
Minus 5.
Plus or minus. Radical.
5
squared.
Minus 4.
Right. So we apply the quadratic formula using our a equals 1, our b equals 5, and our c equals minus 7. This isn't writing properly today for some reason. And then we just simplify this a little bit. It's minus 5 plus or minus the square root. This would be 25 plus,
28.
well, 2 negatives, so that becomes a positive. That's plus 28.
Which will give you 53.
Give you 53. All over 2. And I think it's fine to leave it there. So that would be our x. I want you to notice that these are actually two solutions. You have x could be minus 5 plus the radical of 53 all over 2, or you can have x equals minus 5 minus the radical of 53 all over 2. Of course, there are some contexts in which one would be acceptable and the other would not, but in general, if you're just asked to solve the equation, you take both as possible solutions. Okay? So this plus and minus can split you into two different scenarios. So, well, that one's out of the way. So again, first thing you try to do, try to factor. unfortunately, doesn't factor. So then, second thing is use quadratic form. And you realize that here, you would have A equals 1, B equals 8, C equals 1. What's 8 squared?
64.
64 minus 4, so that's radical 60 over 2. That one can simplify, I think.
Yeah.
How can you break down 60?
5 times 4 times.
Right, so this is 4 times 15. So I can, remember, radicals distribute across products, so I can think of this as the radical of 4 and the radical of 15. Radical of 4 I know is 2. And so a nice way to write this, bless you. Nice way to write this one would just be to, right, divide 2 into each part. Minus 4 plus or minus radical 15. And so that would be your x. And again, notice that these are two solutions. You have minus 4 plus the radical and minus 4 minus the radical. So quadratics aren't that bad. We already know the process. First thing you try to do is solve by factoring. That might require you using the AC method as well as the straightforward method or the trial and error method. A bunch of methods there. Don't apply the zero factor property prematurely. Don't try to divide things out prematurely. Follow the strategy, bring everything to one side, factor, and use the zero factor property. If factoring doesn't work when it comes to quadratics, you have the quadratic formula at your disposal, and that would work in that case. That formula doesn't work for anything. We did it specifically for quadratics, so don't think you can apply the quadratic formula to other things. Okay, it's not going to work. So, other equations we want to be able to solve. Equations involving radicals. They show up pretty often as well. So we don't really have a property of equations that deals with the radical case. That's because you have little nuances that can happen here. Suddenly when radicals are in the mix, things can go wrong because if you take an even radical of a negative number, it's not a real number. Or if you raise both sides to an even power, you can kill negatives and etc. So you kind of have to deal with these separately. So strategy here is to usually you want to isolate the radicals. And raise both sides of the equation. To a convenient power. To kill the radicals. So that would tend to be step 1, step 2. You might have to do this several times. We'll look at some examples where we kind of have to do it several times. Rinse and repeat as needed. Step 3. Solve using previously mentioned techniques. So you'll eventually, after doing this enough times, you'll end up with an equation where there are no radicals present. And so now you just end up in one of the previous cases that we dealt with. There is a step 4, however, which is very important when it comes to radicals. This is kind of a strange one. As I mentioned, because raising to certain powers can change signs and affect how the numbers, what numbers are valid from what aren't, it turns out by doing this process, when you're raising both sides to powers, you can introduce fake solutions. So it's actually very important that you check your answers afterwards. So it's not just a matter of checking to see whether you make a mistake or not, because you can do everything perfect, and yet the answer that you end up with isn't the answer, because you introduce some erroneous solutions. Step 1 can introduce the technical term is extraneous. We mentioned last time it just means fake. Just put solutions up there. So that's basically the process. Usually you want to isolate the radicals. Don't do this if it's more convenient to just start raising things to powers right away. Keep doing this until all the radicals are eliminated, and then just solve the equation by previous techniques. It's very important that after going through all this, you check your answers. So let's do some examples of solving equations with the radicals. Let me just list them here, and we try to knock them out. Examples with radicals. So what do we do here? Square both sides, right. So the radical is already isolated, so we can skip to the squaring both sides section. We have to do both sides. Again, this is another thing that is peculiar to equations. A lot of times students square things randomly. You can't just square things whenever you feel like. There has to be an equation present, and you have to do it to both sides. If you have a radical in an expression and you don't like it, tough luck. You can't just randomly square something because you don't like the fact that there's a radical in there. You can square both sides of an equation. That is a valid thing to do. Okay. If there's no equal sign here, you can't randomly square something because you feel like it. It's very important. Okay, so but squaring both sides, we'll do this, and we will get just 8x minus 1 here equals 9. So now you'll realize that's just a linear equation. We know how to deal with those. Move the 1 over, that will become 10. And then divide both sides by 8. So this becomes 5 over. Now, do not assume that is the solution. You always need to check. So you take the radical of 8 times 5 over 4 minus 1. And so now 8 times this, well, 4 goes at that 2 times, so that's just the radical of 10 minus 1, that's the radical of 9, and that is 3. So the check works out, and I am able to now say that x equals 5 over 4 is the solution. So the moment we got this, we weren't sure yet if this was the solution. When it comes to like raising both sides of the powers, you have to be very careful. And in some of these examples, you'll see why. There are some situations here that you'll see. Again, here's a situation where you can just square both sides to get rid of those radicals. A valid step in an equation is to give us 3 plus x equals x squared plus 1. How do you solve that?
Subtract 3, the 3 left and move to the other side.
So x squared minus x. If I bring over a minus 3, that's plus 1 minus 3, so minus 2.
X minus 2, that's plus 1. X equals 2.
Okay. Now we have to do our check. Check. So now I'm going to check x equals 2. Does that actually work? Well, if I look at the left-hand side, that is the radical of 3 plus 2, which is the radical of 5. If I look at the right-hand side, that is going to be the radical of 2 squared plus 1. That equals 2 radical of 5. So x equals 2 checks out. Now let's go to x equals minus 1. If I plug that into the left-hand side, I would get radical of 3 minus 1, that's equal to radical of 2. If I plug it into the right-hand side, I would get the radical of minus 1 squared plus 1, that is also radical of 2, so this one also checks out. Both of those actually work. So I'd be able to say now the solution is x equals 2 or x equals minus 1. The checking step is very important. The moment you have to solve an equation by raising things to powers, you have to start checking. And be very vigilant, because you can, bad solutions can sneak in. What? What'd you say? I heard someone say where are we now? 1 plus x. Okay, what do we do here? What do you think we do now?
Do you bring one of the radicals to the other side?
Wouldn't you square because of the fact that the radicals, both of them are on one side, so they're already isolated?
Yeah, so I would just square them here. It's not going to make, well, in this situation, it's not going to make much difference if you move one to the other side, but they're already isolated, so I probably won't waste time doing anything. Because you're going to have to, you'll see what I mean after this. What does the square of this side look like now?
One plus x. Plus would it be radical 1 plus x times radical 1 minus x? That makes sense. Is that correct?
Yeah.
Distortion of the wall.
I don't know. What do you guys think? Huh?
Let's keep going, then 1 minus x.
let's just keep going. So here's where you remember, complicated problems are really just simple problems in disguise. What's the simple rule here?
Sum.
What do you think when you see this?
There's a
Sum of
sum.
squares.
Sum square. Where?
The square of a sum.
Square
is the-
sum.
It's this, right?
Which is,
Where this is the A, that's the B. You deal with all of those exactly the same way. It's A squared plus 2AB plus B squared, always. It doesn't matter what A and B are, so there should be a 2 there. Plus, now you square that.
Plus.
Now any of you thought that was just 1 plus x plus 1 minus x, you distribute powers across sums. There you go. This is just an instantiation of that. Okay? It's not like, let's just keep going. No, just know what you're doing is the right thing, right? Right, there's always going to, whenever you look at something you're kind of confused, there's always a simpler rule that would explain what you should do. So don't just think of a simpler version of what you're doing, and then you can work your way back and figure out what you should be doing. So the left side would become this expression. The right side would become 4. Now this guy I can actually simplify a little bit. This becomes 1 minus x squared. Do we see why? Okay. That's weird. Do you see what happened? Because the product of radicals I can just turn into one big radical. Difference of squares applies. So I can combine it into that. Now we go through the process of isolating the radical again. So I still have a radical to deal with here. What I'm going to do is isolate it, bring everyone else over. In fact, right now the x will kill the x, and I would have a 2 from this 1 plus 1 that I can bring to the other side, and I'd be left with a 2 here. So this simplifies to that. I can divide both sides by 2. Simplifies to that. Now we square both sides again. It's more like a simpler version that we did in like part A. So we'll square both sides again. So we're applying a square 2 times. So at this point, square this, square that. So 1 minus x squared equals 1. And so you get x squared is equal to 0. So you get x equals 0. Now we squared up things twice. Definitely don't know if this will be the right thing, so I will definitely do the check. And so what I can do is actually plug in x equal to 0, 1 plus 0 plus 1 minus 0. That's just radical of 1 plus radical of 1. That is equal to 2. So it actually does work. X equals 0 is the only solution to this one. So here we raise it to a convenient power to kill the radicals. A radical still showed up, isolated again, rinse and repeat. Eventually we get to a point where there are no radicals in play and we can solve the equation using previous methods. Again, for emphasis, you have to remember the basic rules. They will always apply no matter how complicated the situation might seem to get. It is never complicated. There's always a simple reason of how you do with it. Anytime you look at something and it looks complicated, it means you're thinking too hard. There's a simple rule for how to deal with it, always. So once we see this, oh, that looks scary. No, it's a plus b all squared. That's not scary at all. I know a formula for that. Boom. This guy now, difference of squares. I know a formula for that. Boom. Then you start isolating square again, and everything works out fine. Let's look at D. What did you do here?
Isolate the radical.
Isolate the radical. I have a radical and a non-radical on one side. Just bring this guy over. Now, want to get rid of that radical, what we're going to do is we're going to square both sides. What does this side square look like?
4x squared minus 4x plus 1.
Well, we're squaring so we can, it's going to kill the negative sign. And what's
So
this
it's
one?
gonna be 2 minus
Just 2
x.
minus x. Okay, so now, this is a quadratic. It's just spread out. So we do our rule, move everything to one side. If you move this over, it'll be a minus 3x. Move the 2 over, it's going to be a minus 1. Does that actually simplify? As in factor?
Well,
Maybe 4x and x, 1 and 1. We want a minus 3, can make it a minus 4 and a plus 1. So this means our x is minus a quarter, or our x is 1. Now let's do our check for each. So if our x is minus a quarter, check it in the original. So I have 2 times minus a quarter equals 1 minus the radical of 2 plus a quarter. Well, I don't know if that's true. Let's do one side at a time. So this is what the So the left-hand side would give us 2 times minus a quarter, which is minus 1/2. The right-hand side would give us 1 minus the radical of 2 plus a quarter. This is 1 minus the radical of 2 I can think of as 8 over 4. So this is 9 over 4. This is 1 minus 3 over 2. So that's 1 minus 1.5, so that's minus 1/2. And that one checks out. If we go with x, equals 1, the left-hand side would give us 2 times 1 equals 2, while the right-hand side would give us 1 minus radical of 2 minus 1. This is 1 minus radical of 1, 0. Oh. This is a fake solution. He snuck in there. Like, we didn't do anything wrong. Right? We applied our rules. So it turns out x equals 1 did not work. This is an extraneous solution. And so it turns out this equation only has one real solution that we care about, and that is x equals minus a quarter. One was an imposter. Okay, so this is why it's important to check. Because you're squaring stuff, you're changing signs every time you square something. So you probably should be getting negative guys, but then this returns a positive guy because you end up squaring somebody. So it's very important with radicals. That's the only thing. Pretty much try to isolate the radicals, raise it to powers to try to kill them, solve using previous techniques, but just be aware that the answers you get might not be the answers. You have to do a check afterwards, and it's super important because when you least expect it, we went through all these examples, everything was great. This last one on the last number had an imposter. So that is equations with radicals. Now I want to talk about another class of equations. We'll see from time to time equations with absolute values. For this, you just need to recall the absolute value of x is x if x is greater than or equal to 0 minus x if x is less than 0. So it always returns a positive number. So you can have absolute value of minus 2 is 2, and at the same time, the absolute value of 2 is also going to be 2. So it shows, this example shows you that sometimes we can have the same answer but the thing inside the absolute values are actually the negatives of each other. But the terms in absolute value signs may have different signs. So that gives you a little nuance that you have to deal with when it comes to absolute values. You have to consider both scenarios. Is the thing inside the absolute values the negative of what I'm seeing, or is it the positive of what I'm seeing? Because both outputs are going to be the same, but you have to sort of consider both possibilities inside the absolute values. So what that really means is that each absolute value equation, you really break it down into two possible equations. So you're given an equation, right? So you have some expression in here in absolute values equals some other expression. Then this breaks down into two possible scenarios. Either you can take the inside expression as is, expression 1 equals expression 2. Or you have to take what's inside the absolute values up as the negative of what you're seeing. Negative of expression 1 equals expression 2. So an absolute value equation breaks down into two possibilities. There's not much more to say than that. I mean, I'll just give you a very simple example. So you might see something like 2x plus 1 in absolute values is equal to 3. And what you have to be aware of is if the inside is positive 3, it will be equal to 3. But also if the inside is negative 3, it will be equal to 3. So you have case 1, where the equation actually 2x plus 1 equals 3, and then you have case 2, in which the 2x plus 1, its negative is going to be equal to 5. Or you can think of it as 2x plus 1 can be 3 or minus 3, and both of those are solved. So this means your x is either, bring this over, 1, or, so this is from case 1. Or your x would be, what, bring the 1 over here, we have minus 4, or x equals minus 2 from case 2. So dealing with absolute values just mean you think of two possibilities. That will actually, when we talk about inequalities, that will actually influence how we do inequalities. But pretty much think of the thing inside as either as you see it or the negative of what you're seeing, and solve for each possibility. So it turns out in either case, if I plug in a 1 here, that gives me 3. If I plug in a minus 2 here, this is going to give me negative 3, but if I take the absolute values, it still gives me 3. So these both are solutions. So there's one other kind of equation I want us to be able to solve, but we will just stop there. Got started late today, so we won't finish this. But first 5 or 10 minutes of next class, we'll be done with this section and move on to inequalities. Shouldn't spend a long time on inequalities. But we'll stop there. I have this in the back, so I'll give you guys that back and we can leave.